This video is for Chapter 2 of CCNA 2 on static routing. We discussed the routing process last chapter, so the next two chapters we have static routing and dynamic routing coming up. Probably the hardest thing we'll see in this chapter, well, depending on your point of view, is summary routes. Aren't that bad, but we're going to have to get back into some binary. So we'll be setting up static routes, going over the advantages, disadvantages, and why you would use a static route within this chapter. Alright, so first part we have static route implementation. So we've already talked about this a little bit, that routes can be learned two ways, either manually or dynamically. So we have a static route that we can set up manually, just like setting up a static IP address on a host device. And we have dynamic routes, and we'll go over how to set those up in Chapter 3. We remember we've discussed EIGRP, OSPF, RIP. Those will be primarily the dynamic routing protocols that we discuss in the next chapter. You've got a couple different static route and default route scenarios. The purpose of them using static routes in this situation is it's going to decrease the entries in your routing table, which means, well, your router doesn't have as many routes to look through. If there's less entries, then therefore making the decision-making process a little bit faster. So you've got R1 connected to these two networks over here. You see it's not connected to anything else other than these two networks on the left side. So if these two networks send traffic that's not going to one network down here or the other, it's always going to be going out this way. So that's when you'd use a default static route, basically saying if it doesn't match this network or that network, everything is going towards R2 over here. From R2's perspective, it's connected to these two networks and the internet. Okay, so it can't just say anything that's not going to these two networks I'm going to send out to R1. It is going to use a normal static route, not a default static route, which would say basically that anything headed towards these two networks goes out towards R1. Okay, that could either be two entries, one entry for one static route for each network, the 10 network and the 11, or you could use a summary route, which is something we'll discuss in a little bit. Basically, a summary route would be a route that encompasses both these networks in one static route statement. So why use static routing? We have a couple pros and cons here and some advantages listed up at the top. So they're not advertised over the network. That's going to result in better security. Dynamic routes are shared by default. Static routes use less bandwidth because you're not constantly sharing routing updates with other routers in your network and your topology. No CPU cycles are used to calculate and communicate routes because you're entering them manually and you're not communicating them. The path a static route uses is known. You typed it in, it's known, it's an entry you made yourself. Dynamic routing protocols, it could be going one way, it could be going another, based on the metric it uses to calculate the best route. So you won't always know which path in a dynamic routing protocol, but you will with static. And you have some differences down here that these are most likely test questions. So pros and cons of static versus dynamic. Configuring complexity increases with network size. Okay, and then this dynamic is usually independent. Topology changes. Dynamic will automatically adapt to a change in your network topology or your network setup. Your static, you're going to have to set it up yourself, because if your topology changes, that's all done manually, so you'll have to go ahead and make adjustments on your own. Scaling, of course, dynamic's going to be better for scaling. It'll go ahead and make the changes it needs to, figure out the routes on its own again. If you're going to scale up with static routing, it's going to be more work for you, so it's more suitable for simple topologies. Less secure, more secure. Resource usage, we talked about that up here. More resource usage for dynamic routing. Static, not as much, no extra resources needed. Predictability, route depends on current topology, route is always the same. So know those differences, pros and cons. They are most likely test questions. So when to use static routing, you've got a couple bullet points here providing ease of routing table maintenance in smaller networks. You really wouldn't go through the trouble of setting up a dynamic routing protocol in a situation like this. You've only got one network behind your router, so setting up a static route off the network and a static route from R2 to the network is going to make sense. Routing to and from a stub network, this is a stub network. So you can see a stub network is a network accessed by a single route. So this connection from R2 to R1. And the router has no neighbors. You don't have a bunch of other networks out here. You just have one network behind your router. It could be actually a couple connected to the same device. But there's only one way off of that general network. Okay, so I shouldn't say multiple networks. You'd have a network or a couple subnets of the same network over here. And you'd have one path to and from that network and its subnets. Okay, so if you have just one edge router here, one way off, that is going to be your stub network. Anything behind this router that doesn't have any neighbors. Single-use default route to represent a path that does to any network that does not have a more specific match within another route in the routing table. So R1, this is not the best example, I guess, but if there were a couple networks over here that R1 had entries to, and maybe you had a 172.16.3, a .4, and a .5 network down here, then you could have entries for those networks that are connected to the router, but anything that doesn't match, you could send out this way. So that's what the default route does. Okay, anything that doesn't have a match in your routing table, that default route's going to go ahead and catch it and send it on its way. So more static route applications. Static routes are used to connect to a specific network, provide a gateway of last resort for a stub network. Again, a gateway of last resort is where do I send something that doesn't match any entry in your routing table. Reduce the number of routes advertised by summarizing several contiguous networks into one static route. Again, we're going to talk about that route summarization process, and we just discussed that static routes are not advertised. Create a backup route in case a primary route link fails. So that's going to be a floating static route that we'll discuss in just a minute. That's going to be a static route that you raise the administrative distance of manually, which is actually a very, very easy process. It's just one number you type in. So this is the same setup we saw a few slides back. So for a standard static route that you have here, that would be the route that R2 is using to connect to R1. Again, a stub network is going to be a network that has a router that has no neighbors. It's kind of a self-contained network. One path off of it, one path to it. So your standard static route would be the route from R2 to R1. It doesn't need to use a dynamic routing protocol. It's always going out serial 000, and its next hop is always this router to get to the network over here, 172.16.3. Okay, so that's always going to be its route to that network. The directly connected network would be the 2 network for R2, so that would be an automatic entry, but you're making a static route to get to the .3.0 network over here. Okay, so that's what you do, standard static route from R2 to R1. But the reverse, if you're trying to get from R1 to R2 or any other network, okay, because, well, R1's directly connected to the .3 network over here, the stub network. The stub router, if it's not going to be, well, if it's not traffic within this network, actually in this situation, then the only other network it knows about is the one that's connected to R2. Any other network can be covered with a default static route, which is 0000 with a /0 CIDR notation or quad 0 subnet mask. That means every other IP address will be sent the direction of this default static route, giving you a gateway of last resort for any traffic that you need to send. Okay, so from R1 to R2, R1 is going to have a default static route that says basically anything IP address 0000/0 or again quad 0 subnet mask is going to be sent out serial 00 towards the next hop R2 here. And that could be going to the internet, it could be going to any other network that is connected to R2. So that's what your default static route is going to do for you. That sets up your gateway of last resort. And we get to a fun slide next. We won't get into it too much just yet, but then you have the concept of summary routes. Okay, so let's take a look at what we've got here. You've got R1 over here connected to, well, there's no label for this router, but you've got 4 networks behind it essentially. Okay, and you're going to want to set up a static route, you've chosen to get to those 4 networks. You could create static routing statements, okay, for each one of those networks. But to get to each one of these networks, you're going the same place from R1 to this first router here. That's the first next hop. That's all R1 needs to worry about. What's the next hop to get to these networks? That's all I'm making a decision on. Where do I send it? Then this router is going to make a decision, okay, I can send it there or I can send it here. That's the router over here's job. R1, all it needs to worry about is where am I sending this initially, then the other routers down the line will make decisions for me. That's kind of like how your home routers work on your home network. Your home network router basically just says, I'm sending this traffic to my internet service provider's router, then it's going to make all kinds of decisions for me. So your home router just has basically a default route saying anything that's not on my home network, I'm sending to the internet service provider's router, and it's going to make decisions. Okay, so not exactly a quad 0 like your home router would be, but here you have 4 networks that you could potentially reach by sending to this router from R1 to this router. You can summarize those all into the same routing statement by using a single summary route that would encompass all of these networks. Okay, this is going to go back to subnetting and a little bit of binary. All right, so basically you've got a /16, okay, which means you have 16 network bits or 16 ones in your subnet mask. And if you take this down to a /14, okay, so you have 14 network bits, you can actually encompass those 16 in that block of 14. And we're going to go over later how you would summarize that, but basically what you do is an ANDing process comparing, well, just the octet that's different. In this case, it's the second octet. Okay, it could be the third octet, could be the fourth, but again, we'll go through that process later. It's not too bad. It might look a little odd at the moment, but we'll talk about it in just a second. And the other concept we will be discussing and how to configure it is a floating static route. That would be a backup route, basically, in case some link were to go down. So in this situation, for instance, you've got your private WAN that you would be using for some company that you would prefer to use because it's your own line, your own leased line. You know how you're getting from one place to another. Essentially, it's going to be faster than the internet. So that would be your first priority. Okay, but you can set a backup in case that fails. Excuse me. That would use your internet to get from branch to your HQ router over here. So essentially how you do that is through setting up a floating static route that has a higher administrative distance, and we'll take a look at how to set that up in just a second. Basically, it's the same as a normal routing statement with a extra number at the end that indicates the value you want to assign to the administrative distance. Okay, so we're going to get into setting up a lot of these things right now. So this next section we are configuring static and default routes, the ones we just talked about, and it's not too bad setting them up. They start with either an IP route or an IPv6 route statement. or command, I should say, if you're setting up either one. So just like any other command, if you want to switch from IP to IPv6, then you just type in IPv6. So here's how the command looks. You type in IP route, then the network address and subnet mask that you're trying to reach. Okay. After that, you've got either, or, and. You could do three different things actually, total. You can type in, after you type in the network address and subnet mask, the IP address of the next hop on the way to that network, or you can type the exit interface. Okay, you can do one or the other, or both, actually. So if we take a look at the next slide, if you type in the next hop IP address, then only the next hop is specified. That's considered a next hop static route. You've got directly connected static routes, which only use the exit interface in the IP route statement. And then you have fully specified static routes, which use the next hop IP address and the exit interface both. You will need to use those in some situations, but generally speaking, the directly connected route is considered to be better than your next hop route in most situations. Okay, because we'll talk about the next hop route, but it has something called a recursive lookup that we'll discuss. Here's how the IP route command would look. So you're on R1 trying to get to the, for instance, 1.0 network up here. Okay, 16.1.0 I should say, and you type in IP route 172.16.1.0, which is the network you're trying to reach along with its subnet mask. And then you're going to type in the next hop IP address in order to get there. So from R1's perspective, you've got R2. R1 and R2, the network between them is 172.16.2.0. R2's address on that network is a .2. Okay, so that's what you're typing in there, is the next hop IP address. Don't get that confused and try to type in the IP address of your router's interface. Okay, you want to be typing in the next hop IP address. Okay, so you've got that. The other way you can write it out is the directly connected statement, which actually is shorter and easier to type out. So you've got IP route. Instead of finishing with the next hop IP address, you're just going to designate the interface on your router that you are going to exit. And that can get, I guess, slightly confusing, because in this statement, or this command, you are going to be using the exit interface on your router. Okay, versus the next hop IP, which is the IP address on the router, but it's the next hop. So interface is going to be on your own device. Of course, next hop IP is the IP of the other device that is your next hop. So remember to keep those things separate. You don't want to try to type in the interface on the next hop device, or the IP address of the interface on your own router. You don't want to reverse those two, essentially. So it's always the interface on your own device. Next hop is the IP address on the device you're communicating with to get to the desired network. Okay. Fully specified route, you've got no example of it here. So a fully specified route is not going to look like this. This is just another example of a static route, or a directly connected route, static route. Directly connected static route. All they have is the interface out here. Okay. If you were going to have a fully specified route, you would have this interface S000 space, then the next hop IP also out there. So that would be your fully specified static route. I don't know why they don't show us that here in the slideshow, but just use your imagination and you can picture an IP address being out here. It's magical. So just put the next hop IP address right after the exit interface as you create your fully specified static route. How do we verify those static routes? You can do a show IP route static, or just a show IP route should be fine too. It'll bring up your routing table, and you'll be able to see those static entries which you have created. All right. You could do a show running config as well. Show IP route for a specific network. Okay. So our interface, it looks like. So you've got those three commands. I'd just say use a show IP route in general, unless your routing table's huge. Then I guess you could limit it to static or connected or whatever limiter you'd like. Okay, but those commands will all be useful. We'll be using those in class. Your default static route, the route that catches anything that is not in the routing table. That is the quad 0 route. So instead of typing in IP route and then some network you're trying to get to, this is for anything that doesn't show up in your routing table. You've got this quad 0 space quad 0 route that basically is a route to the gateway of last resort. Provides a direction for you to send traffic that's not in your routing table, and it's the exact same situation. You can either have a next hop route, a directly connected route, or a fully specified route when you create your IP route. So in this example, they've used the next hop. They've used the next hop IP. So you've got that. Moving right along, I'm just remembering some comments in class about sound effects I make during this video. I've been making them. I'm going to try to stop. Anyhow, let's see what else. Verify a static route. Again, you got IP route static. Same thing we've seen. Gateway of last resort. You can see that quad 0. You can see the gateway of last resort set up based on that default route. So those are things you'll see if your default route is set up correctly. And then we have the IPv6 route command. IPv6 route command, same thing, same exact thing. There's my two sound effects right in a row. There's IPv6 route, type in the network you're trying to get to, and then you can either use the next hop IP address or the exit interface. Same rules as IPv4. Again, same as IPv4 here. And here's a next hop. You just have what you're trying to get to, / whatever the prefix is, and then you have the next hop IP in this example. Directly connected using the interface, just like IPv4. So fully specified static IPv6 routes. You are going to need to use a fully specified IPv6 route if you decide to use link local addresses as your next hop IP. Because, for example, we've got R1 here who's trying to specify a next hop IP of FE80::2 over here. All right. So if your next hop IP is FE80::2 over here, that might not be useful to your router, because each network on your router could have potentially have a FE80::2 on it. These link local addresses are only unique on their specific network. So these two are only unique to the network that connects them. They could have, for instance, R2 off to the right could also have an FE80::2 over here, as this link local could have a FE80::2 on the bottom, FE80::2 at the top. You could have multiple interfaces with FE80::2 on it. R1 could be connected to multiple routers that have FE80::2 as their link local interface that is connected to R1. So let's say that there's a router out here who's also using FE80::2. R1 doesn't know where to send this traffic that matches the network here, because there's two links that are connected to FE80::2. All right? So if you're going to use a link local address, you need to specify the interface that you're exiting out of here. So S000 in this situation. That way you know, okay, it's going out S000. It's headed for FE80::2. So it knows exactly where it's going. All right. In which case, you almost might want to just use the S000 instead of just the link local address. There is a reason to use fully specified routes. I've stated that before, and we'll talk about that in just a second. But not just yet. Verifying IPv6 routes, same thing. Show IPv6 route, show IPv6 route static, same things we saw for IPv4. Okay, default IPv6 route, just like IPv4, you had all zeros. All zeros in IPv6 is : that represents all zeros as your IPv6 address. /0, zero prefix, so that covers every address, just like the quad zero network in IPv4. And an example of how that's set up: IPv6 : 0, and then in this example they use the next hop IP using the global unicast address, not the link local, so they didn't have to fully specify the route. Okay, remember, if you're going to use link local, you're going to have to fully specify. Before we take a look at this slide, I'm going to go back a little bit to look at our next hop static route and why that is not the best technique to use. There we go, there it is. So your next hop static route, I referred to something called a recursive lookup that I thought came up later on in the slides, but it doesn't. So let's talk about it right now. So if you're going to configure a static route with the next hop IP address, that's fine, it works, but your router's going to have to do a little bit more processing to use this next hop route. Reason being is you're telling the router that the next hop is this, but the router still needs to look in its routing table as to which interface it needs to use to get to this next hop IP address. Okay? Whereas, and that's what's referred to as a recursive lookup, looking up this next hop IP address in order to excuse me, in order to send traffic to this network. Okay, so it has to look this up. That's called the recursive lookup, that next hop. You won't need to do that with a directly connected route. Okay, you've just got the interface and it's going to go ahead and send it out of there. No lookup necessary. So not only is it easier to type in because it's just less numbers and letters to type, it also is easier on your router. Okay, it's going to result in faster processing. All right. Now you also will need this this fully specified route. You might ask, why would you ever use a fully specified route if the interface is enough? But there are situations where you may have multiple devices at the end of a port. Okay, so it might not just be one device on the end of a port. So if you have multiple devices, you are going to have to include both I've showed you, not the end of a port, the end of an interface. Let's use the correct terminology. The end of the interface, like the serial or gigabit Ethernet interface. So if you have that situation arise where you have multiple devices at the end of an interface, then you would have to use the interface ID as well as the next hop IP and use that fully specified route that we discussed earlier, where you would type in the interface and the next hop. Only if you have multiple devices at the end of that interface. Okay, but most of the time, I mean, in most situations, the directly connected route is going to be well and good enough. Verify IPv6, so IPv6 route static. Floating static routes. So we discussed this quickly before, but a floating static route is a backup route. You're going to set up these backup routes just in case the desired route or the better route goes down. So the example we had before is that you got this WAN here, it's quicker, it's the better route to go, but perhaps 000, this link goes down. Okay, something's wrong with your connection here. You also can configure a backup route, which is a floating static route that will kick in just in case this link goes down. Okay, to create that, you need to create a route with a higher administrative distance than a normal static route, and that's easy to do, very easy. Basically, or if you remember from chapter 1, a normal static route has an administrative distance of 1. 1 is a very low, it's the most trustworthy administrative distance other than a directly connected route, which is 0. Okay, so if you configure your routing statement with an extra number at the end, same routing statement. So for here we've got, for instance, these are both default routes. One's going this direction up here, which is going to be our desired default route. Okay, but we have another one down here that we potentially can take. And in this example, we're assuming that this link is slower or less desirable than that one. Okay, so our first routing statement here says send everything from this network that needs to get off the network this direction. Okay, but in case this link fails, we've got a backup route here with a 0000000 that's going to send it this direction to the 10.10.10.2 network. This extra 5 at the end means I want to make the administrative distance of this route 5, which is higher than the 1 that would be automatically assigned to our first entry here, which means this 5 will not be used ever if this link is up, okay, because this is our desired route. But in case it goes down, you're going to use this link down here. And you can make it a 5 if you want to make it a backup route for something like EIGRP. You can make it a 95 since EIGRP is 90. So you've got some options there as to how great of an administrative distance you want to give to your floating static route. To test the floating static route, you can verify that it's there in the routing table with a show IP route. If you do a trace route command, you can see the path that the traffic is flowing. And if you want to test that floating static route, you're basically going to disable the link for your primary route and see if the floating static route kicks in. And it should, if you configured it correctly, go ahead and use that backup route if you shut down the link for the primary route. Here we have the concept of automatically installed routes on a host. We've discussed those last chapter as well. They're indicated with the L. Your local routes that come up when you give an IP address to an interface on your device. So those will automatically be entered as soon as that interface has an address. That host route is just for one host. It's not for a network. Okay, so every one of your bits are going to be host bits. Or I should say, whoops, why did that advance? Why are we moving? I don't know. Or actually the converse of that pretty much, because you indicate a host route that's just for one host with a either 32-bit subnet mask or 128-bit prefix or mask in IPv6, which means there's no room, there's no network, it's fully specified. All 32 bits or 128 bits indicate that one host. Okay, so that's what you're going to see, a /32 on your L's or a /128 on your L entries in your routing table for those links. Okay, because it's indicating one host. Okay, one host address. Automatically installs, we already talked about, indicated with the L. You can actually use those host addresses to set up static routes, which we'll see in the next couple slides. Okay, so if you wanted, in this situation, they're using IPv6, you could use IPv4 as well. Do they have an IPv4 entry here also? It doesn't look like, yes they do. All right, cool. So you've got branch here going to the server. All right, so if you want to set up a host route that only communicates with the server's on a network. You got a 64-bit prefix there. You've got a 27-bit CIDR notation there. Okay, so it is on a network, this server, but we're saying the branch doesn't have doesn't have any need to communicate with the network in general. It just wants to communicate with the server and have a entry in its routing table as to how to communicate with the server only. So you're going to use that server's local address, okay, the L address assigned to the interface on your server, okay. What you're going to do to make that happen, you can see its server's address is here exactly, .99, and then you've got the IPv4 address is .238. So for your IPv4 statement, you're going to type in 209.165.200.238, okay, as you normally would, but instead of indicating the network that it's on with a subnet mask that would match a /27, you're just going to make that a /32 with a 255.255.255.255. Okay, that means this address is unique. There's no other room in that network. It's just one address. Okay, so this route's going to this address only because you have that /32. Then you have your normal next hop IP address, which is going to be the IP address of your next hop device here. Okay, and really that is about it. So that's what you have for the IPv4. For IPv6, same situation. You've got the IPv6 address that you're going to write in here that matches this one, and you're going to have a /128, which means this address is unique. It's not a network that has any other addresses in it. Okay, it's just got this one entry. And again, they're using the next hop IP here of the router. So it's the same type of static entry. You're just using a different prefix length. You're using a different subnet mask that contains, well, all network bits for the most part. It is all network bits, which means this is the only address available. Okay, you can't communicate with the 27 network in general. Can't communicate with this /64 network in general. Only these interfaces, only these addresses are going to be able to be communicated with in your routing table. So you can see how that shows up in your routing table down here. You've got your static route that we created, okay, and how you get there. And down here you have the same thing, static route we created and how you get there. Okay, so that's configuring a host route, and there's how you do it with a link local. Remember, with a link local address, you do need to use the exit interface and the link local address. Okay. And we have our last section here, which is actually pretty dang short. So, troubleshooting default, static and default routes. Same thing we've seen for other troubleshooting exercises. You're going to use your ping, use your trace route to see where issues are taking place. Ping is good. It'll show you if you have communication, but a trace route's going to tell you exactly where the communication broke down, or a tracer T on a host device. So is it worth it to ping? I guess, but if it fails, you're going to have to do a trace route anyway, most likely, or trace T, RT I should say, or trace whatever, however you want to call it, to figure out which router is down or where the issue is taking place. So maybe do a trace route from the beginning. Okay, incorrect route statements can cause problems, conflicting routes in the routing table. So we'll see a couple of those things in the lab. Then we have the chapter summary down here, and we didn't talk about route summarization now, did we? I guess we can go back and do that now. I'm going to back up a little bit, and then we'll do a quick exercise on route summarization. I don't even think it comes up in this chapter's test, but it's something we should know. Okay. So here we have this summary route. It turns out, looks like you won't have to do any route summarization in this chapter as far as testing and labs go, but it is useful to know how it's done. So this summary route that encompasses all of these routes, okay, how is that calculated? You're basically doing an ANDing process, and figuring out what the network address and subnet mask are for the summary. Okay, so we have a /16. That means that we have all of our bits turned on in the third octet here. That's the octet we would be working in to figure out our summary address. And here's how you do it, ANDing process. It's going to bring up our chart here, and here it is. Okay, so we had these 4 networks on the slide. All right, we need to figure out, well, what the summary route is for those. The instructions that used to be in the readings, which don't look like they're in the readings anymore, would tell you to take these, and I'll break this entire address, both 4 of these addresses, down into binary and then compare them and contrast them and get your answer. But we don't need to do that. We don't need to do that. All you're going to need to do to create a summary route is take your highest entry in your range and your lowest entry, compare the bits of the octet that you're working in this case the third, and you'll be able to figure out your summary route. So for instance here, we've got 20 is the top, 23 is the bottom. Okay, so what do we do to get a 20? We go 0 there, 0, 0. Okay, 20 minus 16 works, so we put a 1 there. It leaves us with 4, got a 0. 4 minus 4, 0. Bam, bam. Okay, so you got that. Then we go down to the 23. Go down to the 23. It's going to be basically the same thing, 0, 0, 0. And we got a 1 here. That leaves us with 7, right? So, no, yes, yes, yes. All right, so that's the top entry here and the bottom entry here. The third octet in binary, that 20 and that 23 in binary. Okay, so where do they match? They match all the way up to this point here. So they match all the way through there. All right, do not match here. I'll just shrink those down. There. I hope that makes it clear. So what we're going to do is compare these. Okay, and if we do compare these, we see that, well, you're going to end up with exactly 20, 0, 0, 0, 1, 0, 1, 0, 0. All the rest would be zeros over here. So the address we're going to start out with is 172.20.0.0. Okay, that's going to be the network that we summarize, but what is the subnet mask? Well, we just have to ask ourselves how many of these bits match. Okay, 1, 2, 3, 4, 5, 6. All right, that's 6 plus the 8 in this octet here that all match is going to be 14. So this would be a /14 address. So I don't know where that second period came from. Probably because I typed it by accident. There we go. So our summary address is 172.20.0.0/14. Okay. Our block size there is going to be 4. All right, so that's 0 to 23. That's exactly the correct block size. So that's exactly what we want to summarize those addresses. So if we take a look, that should be exactly what they got. Yes, 172.20.0.0/14. So you're going to compare those bits, top and bottom address, or highest and lowest address. How many match? You can use that for your CIDR notation, your subnet mask. And that's going to be how you summarize addresses. Okay. That's not on your, again, not on your test, but something you probably want to know how to do is summarize. I don't think looking at the materials, doesn't look like it's in CCNA 2 anymore that we use do any summarization on our own, but that's how you would do it. Okay. So that's going to be it until next chapter, where we start dynamic routing.